So it's amazing to have Tristan Wells here with us today. Tristan is currently finalising his PhD at Codes, and his research is focused on magmatic fertility and vectors to porphyry mineralisation in the Macquarie Arc. And he'll be chatting to us about his work on geochemical indicators of fertile porphyry systems in the Northparkes District. So it's going to be an awesome session. Please use the chat. You'll have the chance to jump off mute and we'll have some discussions at the end. And yeah, I hope you all enjoy it. So thanks so much, Tristan, for getting involved.
Awesome. All right. Thanks very much for coming and listening. It's a bit unique to be talking to a computer screen in an exploration office, but I'm sure I'll cope with it. So some people may have seen this talk before. I gave it at a Swedge meeting a while ago, and sorry for those of you that are going to get bored, but work's getting in the way of academia at the moment. So just take a quick moment to acknowledge my PhD supervisors, Seb Meffre, Dave Cooke, who's given one of these talks himself, and Jeff Stedman. And the research was part of a broader study on the Lachlan Arc, so the Lachlan Arc linkage with the numerous sponsors down there, the main one being CMOC Northparkes, obviously letting me play around with their rocks, but we'll get into it. So the geochemical indicators of fertile porphyry systems in the Northparkes District and what we can make of it. Yeah. So just as a brief presentation outline, I'll go through a very quick district overview, touch on some of the geochemistry. I won't go into that detail too much. And then into the actual interesting stuff, or well, I think it's interesting at least. So fertility indicators from geochemistry, whether or not we can assess them with a pXRF, and how pXRF isn't such a dirty word sometimes. And then a little bit of mineral chemistry, and I won't do green rock, but I'll do apatite mineral chemistry. It's a little bit different, and it's definitely in its infancy, but I'll go through it anyway. So a quick overview of this part of the world. Most people are pretty familiar with the Macquarie Arc. So yeah, 4 division volcanic belts separated by pretty much turbidite sequences for the most part, and economic porphyry mineralisation is pretty much confined to the western and central belts. Not saying that there's not stuff going on in the Rockley-Golgon and Kiandra belts, but the Junior Narromine and the Molong belts are more renowned for their porphyry systems. There's a whole bunch of skarns and epithermal stuff and mesothermal and all those other interesting and juicy things, but for the sake of this talk, it'll be all porphyries. And the relationship between the volcanic belts themselves, pretty complicated. Lots of theories postulated. A PhD coming out of Codes in the next 12 months by Tom Sharp goes some way to refining some of those using their physics and strain rates and all that kind of stuff to help nail that down a bit. So when that becomes publicly available for anyone interested in exploring in the Macquarie Arc, might be a good one to look into, or hit up Tom himself. I think he's still down there. So, yep. So the Northparkes District itself, about 350 k's west of Sydney. Long history of mining and exploration in the area. So mineralisation as alluvial gold, first reported in the 1800s by the GL survey, or what was the equivalent of the GL survey back then. And it's hosted by the Ordovician Ganumbla volcanic complex. And there's a photo there of what the land looked like during the drought. It definitely doesn't look like that at the moment. If you tried to stand in that paddock, you'd be probably up to your knees in water and up to your eyeballs in mosquitoes. They're unbelievable out here at the moment. So the Ganumbla volcanic complex, comprised of 3 units, the Nulungalus, which are pretty much inert, well, not inert, but they're not mineralised, at least not well mineralised. The Ganumblas themselves, which host the majority of mineralisation at Northparkes, and the Wombans, which form a thin skin over the top. So exploring in this part of the world, if I drilled into the Womban volcanics, I'd be pretty excited about the erosional level and hoping I could get to the Ganumblas, where the good stuff might be, if I'm lucky. And they're a sequence of high K calc-alkaline to shoshonitic andesite, trachyandesites. Yeah, breccias, volcanoclastics, the usual stuff. Yeah, I don't deal too much with volcanic rocks themselves, well, volcaniclastic rocks, but they're there. So the Northparkes Porphyries, 5, arguably more, major porphyry centres on a northwest-southeast trending linear that's probably closer to 6 kilometres long than 4 kilometres. And there's at least 7 intrusive phases, but again, probably more. They're very, very similar in terms of mineralogy, texture, and chemistry. They all look and taste pretty similar too. So they are alkalic and transitional calc-alkalic porphyry systems. They kind of sit on the cusp of that cutoff, and the mineralisation is more akin to the alkalic style of mineralisation, but there's definitely some evidence knocking around for calc-alkalic sort of things. And there's 2 discrete mineralising events. So an early epithermal flavoured mineralisation event that's been overprinted by a later porphyry event, and there's a guy that wrote a paper on that earlier this year. If you want to look that up, it's in AJES. So the rocks themselves are very, very similar. I haven't put a gravity image on the map itself, but up around that area where E27, E22, E48 are, where the mines are, there's a large gravity low, and that's a product of a composite stock, which is, there's an example there is the E27 biotite quartz monzonite. And that's texturally variable, but it's quite large. It takes up a fair volume of that area of the world. And these rocks have actually been picked for their dissimilarities. So when logging these things, sometimes it can be pretty tough to pick the contacts between them. And there's not too many rock pictures in this one, so if you're here for rock pictures, enjoy these. But the things we're actually out here looking for are the E27 K-feldspar augite ferric quartz monzonite porphyry, or KAQMP for short, or if you want to use the mine sort of terminology, it'd be porphyry 2, which rolls off the tongue a bit easier than the other 2. And that's, you know, it's the lesser of the 2 mineralising intrusions. It does have quartz bornite or quartz chalcopyrite veins in it, and it just has typically a lower vein abundance than the really juicy things, which is the E26 K-feldspar quartz monzonite porphyry, or KQMP. And that example is pretty altered and has nice, you know, quartz bornite stockwork veins with potentially a little bit of biotite as the only mafics compared to the augite ferric quartz monzonite porphyry. The other interesting rocks that occur in the district, the example there, the 230 porphyry, if you'd seen that in the mining sequence, because that's about 15 kilometres away to the southwest, if you'd seen that in the mine sequence, you would have called it a 0 porphyry or a late porphyry, and it doesn't carry any grade in the mine sequence. But yeah, 16 k's to the south, it's about, I think, 8 million years older than the other porphyries off the top of my head. So it's early and it carries a little bit of grade, and it's the progenitor to a large mineralised magmatic hydrothermal breccia. So complicated area of the world, lots of things going on, and a prolonged intrusive history over the 16 kilometre space. So yeah, the rocks, they're interesting, they're a little different, and chemically not all that different in the long run. Anyway, so Northparkes sampling, this is just to give you an idea of what I did during my PhD. So 58 full characterization assays by the usual methods, so XRF and some, you know, wet chemistry, a little bit of leco, and a couple of ore grade samples, but I tried to avoid them where I could, and then followed that up with pXRF, so 263 comparative analysis on the same rocks, so 3 to 4 analysis on each rock. Yep, and that was mainly to overcome textural issues when I was using rock samples themselves. And I just used an Olympus Fanta, but you could do the same thing with, you know, a Niton or whatever. So here's an example of what you don't do in altered terrains. They're using total alkali and silica, but it's more to point out that the mineralising intrusions, which are the ones in the warm colours, the orange and the red, are more evolved, and that's about it really. And you know, further examples of what not to include in your assay suite. So there's a bunch of samples there that are trending towards 100% silica, and they're from historic work from a thesis I won't name, but that's quite heavily veined and probably shouldn't have been submitted for that kind of analysis at least. But the key takeaway is the warm colours are the mineralising intrusions. In terms of spider diagrams or multi-element diagrams, they are arc-related rocks, so they've got, you know, the thorium is relatively positive. They've got niobium, tantalum anomalies tending towards a negative, and yttrium is pretty low. So they are arc-related or subduction-related rocks, which is, you know, pretty much what you expect in this area of the world anyway, but it's just to give people an idea of what the general trends are. Again, nothing outstanding in some of the major elements, you know, kind of what you expect, compatible behavior, and calcium potentially a little bit interesting, but nothing outstanding. It's nice fractionation trends. Spread of data in the alkali metals is kind of what you expect given the abundance of, you know, potassic and albitic alteration knocking around this part of the world. Manganese is an interesting one. There's, you know, an argument for an inflection point, and it does, you know, tend to drop right off there, and some potential for both manganese and phosphorus to be indicators of, you know, fertile porphyries given their, you know, reduced abundance at that area. So where you get above sort of 65% silica, you're more evolved. You really do have a bit of a step there, but it wasn't strong enough at the time for me to make a case for it. So I'll move on. In terms of alteration in these rocks, there is a little bit of potassic alteration. The least altered rocks plot kind of where you'd expect them to for alkalic rocks. I didn't plot the trend on there, but I should have. And you have to remember with these plots that, you know, there's potential for overprinting. So anything that's potassically altered might retrogress back towards albite or be pushed out towards muscovite as well, and weathering affects that too. But for the most part, they're not that altered, with the exception of, you know, a few that have got a bit of potassic alteration knocking around, which is a good thing given that that's what we're looking for. Where it got interesting was when I tried to separate out some heavy minerals. So I could separate out titanite, which was good, but I couldn't find any zircons. And the whole point of the start of my PhD, at least, was to try and find zircons and date things, and then see if I could do zircon mineral chemistry to see if I could vector from that. And I spent a long time trying to separate things, and got to the point that I was going to quit my PhD because I didn't think I was very good. And it turns out that there was no zirconium in these rocks, or very low zirconium, therefore not many zircons. So it was fortuitous, but it became interesting. So if you take notice of the zirconium over silica plot, it's everything in the warm colors that plots in that low zirconium trend. They're all the mineralizing intrusions, which I didn't notice at the time, but after I tried to separate the zircons, it stood out pretty well, and it stands out pretty well in the other immobile element plots. So I kind of ran with it, see what I could develop out of it. And when I plotted it back on the immobile elements diagram, yeah, it stood out pretty well that these mineralizing intrusions had a low angle trend compared to regional fractionation. And I had some discussions with Bob Laux and a few others about, you know, what was causing it. And we came to the conclusion that it was water content, essentially. So the high magmatic water content was causing zircon to saturate early, which is, you know, a nice indication. So to have hydrous, potentially all forming conditions, we need a lot of water, and by having a lot of water, we're, you know, crystallizing zircons early in the sequence, so saturating early, and that's the result. So if you look at just zirconium over silica, it really does stand out pretty well. The issue that I ran into was silica is not in a lot of exploration data sets. You don't typically assay for it. So I needed some other indicator, but I'll get to that a little later. So to prove to myself that I wasn't, a terrible geologist and academic, and that I could, at least pan zircons, I took some half-inch round mounts to the scanning electron microscope and did some mineral liberation analysis to make sure I could actually find some zircons in these rocks. And they don't stand out real well in the top one, but you'll have to take it on faith that there are some zircons in there, but they were actually too small for laser ablation, uranium lead dating. They were smaller than the diameter of the laser beam in most instances. There was a couple of larger ones, but I wouldn't have got a statistical sample, so I couldn't actually date most of these mineralizing intrusions anyway. But at least I had some evidence that I wasn't terrible at panning zircon. So stepping into whole rock fertility indicators, falling back on the work of Bob Laux and Castillo and Jeremy Richards, I looked at strontium, yttrium over yttrium. So yttrium content reflects hornblende fractionation, and the strontium yttrium ratio is the suppression of plagioclase in favour of more hydrous phases. So hornblende and clinopyroxene titanomagnetite to a degree, which is, Scott Halley's covered off pretty well in his talk as well. Oh, not pretty well, very well. And of course, these rocks are alkalic, so instead of being hornblende, it's more clinopyroxene biotite flavoured thing. So strontium over yttrium does work in alkalic rocks. It's not ideal, but it definitely works. And those mineralising intrusions do plot in that field, which is great. The issue with strontium is that it's very, very, very mobile. So any kind of alteration really does move strontium around. So anything greater than 3% loss on ignition, strontium's going to be mobile. And in terms of a visual indicator of that, if you can't observe plagioclase twinning, then your loss on ignition is probably greater than 3%, and you've definitely moved some strontium around somewhere. So there are issues with that, but it definitely works. On the right, that's just a complicated way, really, of showing a rare earth element curve. So looking for things to be driven upwards. So you've got light rare earths greater than the middle rare earths, which will push things up the y-axis, and then mid rare earths greater than, less than heavy rare earths will shift it to the left. So it's just a complicated way of showing something simple. I'm not actually sure why I put that figure in there, but it's there anyway. The simple way to do it would be to plot a rare earth element curve. So we're looking for a listric or a spoon-shaped curve. And this is all from the 58 samples. So that's all the data from across the district. And then if you keep an eye on the scale on the left-hand side, these are the mineralizing intrusions. So overall, a depletion in the rare earth elements in total, but a nice listric shaped curve where the mid rare earths are depleted relative to the light and slightly to the heavy. So I'll go back a slide and you can see that scale change. So quite a lot of depletion overall. So that's the kind of signature we're looking for. It indicates hornblende fractionation, titanite, potentially garnet, but if you plot up dicprosium and ytterbium over silica, you can see that garnet's not involved too much, which is a nice test. So I thought, well, I know zirconium is picking those mineralizing intrusions, and I know that yttrium works well for hornblende or clinopyroxene, so I combined the two, and discovered a nice little indicator of magmatic fertility at Northparkes, and it's between 95 and 100% successful, depending on what samples I run and how good my logging is, really. So yeah, that was what I came up with, pretty much by chance, because I couldn't pan zircons. So we've got hornblende / clinopyroxene ferric rocks that have low zirconium content, and they're both due to elevated magmatic water content. The benefit of using zirconium and yttrium is they're both immobile. So it doesn't matter how much you alter the rocks, they should be pretty stable and happy. The only thing that would really knock them around is volume addition, where you got a lot of veining and stuff like that going on. But that should be captured in your data anyway. So yeah. So I thought, well, that's good. It works at Northparkes. Maybe I should try and apply it to a global data set that I compiled with the help of Bob Laux and a few other people. A lot of sampling stuff taken from academic papers and published papers and PhD thesis. But I just coloured everything up for the strontium yttrium over yttrium diagram just for where it sat in that field, and that was just my baseline, given that that was the current standard for testing magmatic fertility. And then ran a comparison with another element ratio that I devised with the help of Bob Laux again, and that was zirconium multiplied by yttrium over aluminium titanium, which is just zirconium multiplied by yttrium was showing the greater difference between the two. So if I had two low numbers, then multiplying them should give me a really low number and increase that difference. And then aluminium titanium is another fractionation and hydrous indicator. So statistically, I think from the global data set, from the top of my head, I think it was 77% successful in picking mineralizing intrusions. And I think the zirconium, yttrium, and aluminium titanium was about 78%, somewhere along those lines, regardless of alteration intensity and stuff, because where I used the data, I made sure that I captured the loss on ignition as well. In comparison, just straight zirconium on yttrium plots captured, I think it was 83%. So it's actually a pretty good indicator of magmatic fertility on a global scale, which was interesting. And I'd like to run more, data through it and make sure it's actually that viable and that successful, because I know one test doesn't really, tell the tale and make it a fact, but early indications are that it's pretty reliable. So to give you an idea of where some of that data has come from, some of it's from Fiji, Red Chris and Baghdad, Chuquicamata, and so it is a truly global data set. It covers off alkalic and calc-alkalic rocks, and the way the chemistry works, this would actually work better in calc-alkalic rocks than it would in alkalic ones. But it works fine in both, so that's good, I guess. As an interesting further test, I ran it through the Geological Survey of New South Wales publicly available data set. Filtered as best I could. I think a few things have snuck through. I think stuff down around the cool serpentinite probably snuck in there somehow, I'm not real sure, but ran the same boundaries. So I think it was 125 parts per million zirconium down to about 50, and then yttrium up to about 15 parts per million, and put those in as parameters for perspective, and then mixed in barren from there. And it highlights areas of mineralisation pretty well, which is interesting. And they're not all Ordovician. There's some Devonian and some other stuff in there too. So as a first pass test, it looks like it works pretty well at highlighting where areas of known mineralisation are at least. So I've done a fair bit of work for juniors, and being a PhD student kind of teaches you how to live cheaply. So I thought, well, that's great. How can I, run the same analysis but make it cheaper? And pXRF kind of stood out. I know they're expensive units to buy, but once you've bought them, the analysis is pretty much free. So there's plenty of work being done on the methods and procedures for how to best use a pXRF. So Fisher and Gaisley and Aisha Ahmed's paper cover it off all pretty well. The workflow for dealing with the data you collect from a pXRF can take a little while to develop. I wrote a Python script with a fair bit of help for data correction, and it took me a few weeks. But now that it's done, my data correction takes, a couple of minutes rather than a couple of hours at the end of the day. So once you get it all set up, it's actually pretty straightforward. How I went about it, I just used an Olympus Founder, but like I said, you could use whatever you wanted to. Operated in geochem mode with 2 beam intervals at about 30 seconds, and that's just a trade-off between accuracy and time. We're all a bit time poor at the moment, so the shorter the better, but that seemed to be the sweet spot. Yeah, and just how you normally use a pXRF really. Pre-analysis calibration check and standards. If you're not collecting standards with the pXRF, you probably should be. Collecting the standards every 10 to 15 analysis is probably great if you're academic. If you're doing exploration at the start of the day and the end of the day, it's probably, fine. Be good if you collect one in the middle to correct for drift. But if you're pressed for time and you've got fieldies doing stuff, then yeah, start of the day, end of the day, sweet. And then avoid, megacrystal veins, vugs, and patchy alteration. Apatite in particular can hold a fair bit of strontium. So it's always good to try and be consistent with what you're analysing. Texture plays a big part. So workflow, and this again is based off Fisher, Gazeley, and Ahmed's work. And I won't go through it too much. It's pretty straightforward. So yeah, analyze your standards. Let the pXRF reach an operational temperature. It's pretty, it's pretty good at this time of year, but in winter and orange, it can take a little while to warm up in the sheds. Yeah, pretty nice to be standing next to a pXRF when it's probably the warmest thing in the room. Run a silica blank and then start your run and go from there, and treat it pretty much like you treat any sampling regime really. At the end of the day, export the data, separate it into 3 files, calculate some correction factors, so linear correction factors, fine. Correct the data, and you can assess magmatic fertility, but I'll get to that in a minute, and then update logs and inform drilling if you're quick enough. Couple of caveats or things to watch out for is that sampling media and battery charge affect performance. We generally use a workstation, which kind of gets around the battery charge side of things. There is a little bit of a lag with the operating temperature. It's a lot better now than what it used to be. The development of the workflow takes a little bit of time, and it helps if you can write code, which I can't, but my mates can, so that was good. Thanks, Osti. And lighter elements are attenuated by media, so you have to, be consistent with what you're analysing through, I guess, to a point. And, you can analyse the standards through the same media or not. Depends what you want to do with your data, really, but it's good if you can. So in order to assess or compare wet chemistry or XRF chemistry to portable XRF, I plotted up the same strontium on yttrium on yttrium plot and just coloured it up for the fields that they were in. So that's the straight ICP-MS data. Rock and pulp samples are obviously the same, so you hope that they overprint each other, which they do. And then pXRF analysis of the same rocks. You end up with a pretty good hit rate. Rock samples tend to wander a bit more than the pulp ones do, but again, that's the product of the texture of the rocks. And then tested, excuse me, tested zirconium over yttrium to see if I get similar results, and these are coloured up from that previous graph as well. And then running the pXRF over those, so that's the ICP-MS data there. pXRF data, yeah, there's a little more spread, but it's still pretty reliable. And the hit rate's pretty good, and it's the same thing again. Zircons tend to be pretty nuggety little things, so if you miss them, you miss them. It's just a textural complexity thing. In terms of how it went in the Northparkes rocks, the mineralising intrusions, for the most part, plot down in that field. So magmatic fertility can be assessed using your pXRF, provided you correct the data. So I'm not saying it's the be all and end all, but if you need a quick and dirty tool, yeah, it works fine. Also ran a bunch of other fertility indicators, Bob Loux's on Jeremy Richards, strontium yttrium on yttrium. Again, that worked pretty well. Strontium manganese on strontium yttrium from Aisha Ahmed's paper. The other zirconium plots down the bottom of the same ones as previous. So they all work pretty well. The issue with strontium is its mobility, and it's, you know, hard to tell how altered a rock is sometimes. And manganese will move around a little bit too, but, you know, Aisha's diagram, the strontium manganese on strontium yttrium, still puts Northparkes in a prospective field, which is absolutely true. It is prospective, so it's not wrong. So the other work I did is apatite sampling. To look at its mineral chemistry, I tried to date it as well, but I didn't have a great deal of success dating it. 34 grain mounts, too many cathodoluminescent images to count, really. Microprobe and laser ablation done in that order, from least destructive to most destructive. And then I sampled all across the district from a whole bunch of, you know, sub-economic and barren porphyry systems, as well as the mineralising intrusion in the mine sequence. So as a quick refresher, apatite is actually a group of minerals. For the most part, they're, you know, calcium, phosphorus, and fluorine. But yeah, so they're fluoroapatite mainly around Northparkes. You don't see too many hydroxyl knocking around. And it's a geochemical sponge. It's actually a pretty complicated little mineral. Yeah, I didn't realise what I was getting into, but it worked out okay. So the first step was colour cathodoluminescence, simultaneous capture of colour CL, backscatter, and secondary electron images. The method, yeah, rastering the beam over the grains and focusing off the grains so you don't cause damage to them. And I came up with a couple of consistent things, and they're sort of what I expected, because the work was based off Fawad Bazari's work in Canada in 2016. So I'd noticed that there was, you know, these nice, clean, happy magmatic apatite, which is the lower left-hand colour CL image, the pale blue, and then some really, really unhappy looking bright coloured apatite grains, which is the upper right colour CL image with a couple of inclusions in it, and, you know, complex internal zonation, which turned out to be a direct reflection of the chemistry, which is also kind of what I expected, but I was testing a theory. So apatite from E26 and the foam box prospect were both depleted in cerium and neodymium and calcium, and enriched in manganese. And there's a little bit of enrichment in strontium knocking around too, which is interesting. And it seems to be concurrent with the calcium depletion. So as a quick interpretation, it was inferred that maybe it's the product of plagioclase destructive alteration, but don't have any evidence to back that up, really. It's more of a quick interp than anything else. So the green to yellow luminescence was pretty well always associated with cerium and neodymium depletion, and sometimes associated with elevated strontium manganese. Dark brown luminescent areas, we think, are related to high magnesium and iron content, but most of the time those areas are too small to actually analyse individually, so you'd get some bleed across from other things, so I'm not real sure on that one. And overall, that ragged green luminescence with a complex internal zonation is interpreted as being the product of hydrothermal alteration, and that cerium and neodymium depletion has been noticed elsewhere as well. So I decided that I'd compare two of the same lithologies, one more altered than the other, and then compare the apatite from those rocks as well. So the apatite chemistry is in the box plots, and the Wholerock assay is in the line work, with the blue rock being the less altered and the green being the more altered. It's a complex diagram, I know, but we'll get there in the end. All right, so Yttrium is depleted in Wholerock, as well as the some light rare earths, and that's true across the board. So the yttrium depletion in Wholerock is reflected in Apatite, and a similar thing happens with all the light rare earth elements, which is interesting. The other trace elements, sodium, arsenic, and tungsten, have an inverse relationship, so they're elevated in more altered rocks and depleted in Apatite. And then another interesting one was a europium anomaly, which has been noticed elsewhere in the world as well. So Olympic Dam, when you get close to ore zones, you see significant increases in europium. I can't remember the paper now, but there was a paper on it. And other things move around a bit, but there wasn't a great deal of consistency in those, so I won't discuss those too much. So in order to define hydrothermal apatite from magmatic apatite, the key thing was the low sum of light rare earth elements. There was this consistent depletion. With the other elements, it seems to be more of a case-by-case basis. So E26 had depleted arsenic and enriched manganese and sodium, whereas E44, which is 16 kilometres away to the south, is still mineralised, but had enriched arsenic and depleted sodium, and manganese hadn't really moved that much from everything else. But the interpretation is it's dependent on fluid source, but the fluids are depleting the rare earth elements consistently, but the other trace elements are changing dependent on that fluid chemistry. Another interesting finding was that the europium anomalies, spiked. There were really strong positive europium anomalies at E26, but particularly around high-grade zones. And the depletion in the other rare earth elements was quite strong where you see that europium enrichment. So the point of all the apatite chemistry and cathodoluminescence was to test apatite as a vector to mineralisation. And I tried it in a couple of ways. So all the apatite towards the cupola up at the apex of the E26 porphyry were recrystallised. So they had that complex internal zonation and bright green colour cathodoluminescence, which is really good in this part of the world. We've got so much cover. It's not massive amounts, but it's enough to stop you from going out mapping. So if you can bounce an air core rig off the top of a porphyry system, you might not find the copper, but you might find a whole bunch of altered apatite if you've got the time and the money to do colour CL. And you find a whole bunch of recrystallised and hydrothermally altered apatite, you might be sitting on top of the next E26, which would be nice. The light rare earth elements are more depleted with proximity to the top of E26, so they increase the number of light rare earth element depleted apatite increases towards the top. And then strontium, manganese, and sodium increase as you move inwards, which is interesting as well. And probably the key takeaway was that the number of altered apatite decreases with depth. So you're really looking at the fluid outflow, cupola points as being the best areas to find those altered apatite grains. So I'll wrap it up there. But yeah, geochemical fertility. So zirconium over yttrium and the other derived zirconium-based fertility indicator, really, really useful indicators of fertility at Northparkes. And they're a product of favourable ore forming conditions, so hydrous, oxidised, that are applicable on a global scale, which is, a useful finding. I mean, you could argue that the copper is where the copper is, and I can pretty much hear people saying it now. But if you happen to tag one of these intrusions in, an air core hole or an RC hole, and you don't have copper there, then you've got an indication that you've got at least a fertile intrusion at depth, or potentially fertile, at least hydrous. And you can assess it reasonably reliably with, pretty standard exploration assay or with the pXRF. which is, beneficial, and you don't have to be too concerned about the mobility of those elements either. And apatite has significant potential as an indicator of mineralisation at Northparkes too, which is a nice finding and, surprised me. In apatite, you're really looking for that light rare earth element depletion and the characteristic green-yellow colour cathodoluminescent response that comes with it. I think the other elements, so sodium, strontium and manganese, it's useful as an indicator of proximity to E26, but I think they need to be considered on a case-by-case basis. Yeah, all right, I'll leave it there and open it up to discussion, and hopefully I can answer some of your questions if you have any.
Thanks so much, Tristan. I really, really appreciate you getting involved.